To build a cyclohexane model, you need 6 sp3 hybridized carbon atoms, the black atoms with 4 prongs, 18 bonds, these are your gray tubes, 12 hydrogen atoms, the white atoms.
Start by connecting the sp3 hybridized carbon atoms in a ring. This ring will have a 3-dimensional structure and will not be able to lay flat on the table.
We will be building the chair conformation of cyclohexane. There are other conformations, such as the boat conformation. But the chair conformation is the most stable because it induces the least strain on the bonds.
It is named a chair conformation because it looks like a lounge chair with a back and footrest.
After creating a ring of carbon atoms, attach 2 more bonds to each carbon. Attach a hydrogen atom on the other end of each bond.
Your structure should stand on 3 legs, with another 3 legs pointing straight up in the air. These are your axial positions. The bonds that alternate pointing slightly up and down around the circle are known as the equatorial positions. You can use different colors for axial and equatorial hydrogens to make it easier to visualize.
Now that we have built a cyclohexane model, we can use it to recognize cis and trans isomers. Each carbon has 1 bond in the equatorial position and 1 bond in the axial position. The axial positions point up and down very clearly, while the equatorial positions point up and down slightly.
Because the ring structures do not allow for complete freedom of rotation, there are 2 isomers for compounds with the same substituents. Thus, cis, Latin for on the same side, and trans, Latin for across, are used to differentiate the 2 structures. You can easily distinguish between cis and trans structures.
Remember that each carbon atom has a bond pointing to some degree up and to some degree down. Whether it's in the axial or equatorial position, every bond has an associated direction. For cis isomers, the substituents point in the same direction, either both up or both down. For trans isomers, the substituents point in different directions, one up and one down. Flipping the ring gives you the same isomer. Just as when you flip a quarter, it remains a quarter.
Let's work on an example together. Take your cyclohexane model and place a methyl substituent in an equatorial position that points down.
Next, place an ethyl substituent on an equatorial position directly next to the first substituent.
Now, is this a trans or cis isomer? Notice how the methyl points down, while the ethyl points up. Hence, since the 2 groups point in different directions, this represents a trans isomer. Trans 1-ethyl 2-methyl cyclohexane.
Now, while keeping the substituents on positions 1 and 2 on the cyclohexane, rearrange the substituents to make this a cis isomer. Alright, let's see how we can make this a cis isomer. For this isomer to be cis, we need the substituents to be pointing in the same direction. We can do this by switching one of the two substituents to the axial position. If we move the ethyl substituent, both substituents will be pointing down. Now we have a cis isomer. Cis, 1-ethyl, 2-methyl cyclohexane.
If we moved the methyl, keeping the ethyl in the same position, both of them would be pointing up.
Let's try one last example. Move the methyl substituent over so there is one carbon in between the methyl and ethyl substituents. Place it in the axial position. Does this represent a cis or trans isomer?
Here, both atoms point upward. Hence, we have a cis isomer. Cis 1-ethyl, 3-methyl cyclohexane.
When determining cis and trans isomerism, if you build a model, you can easily distinguish between the two.